Hello students, welcome to another video of our engineering physics series. Today we will discuss about Schrödinger's wave equation. In our syllabus we have time dependent Schrödinger's wave equation as well as time independent Schrödinger's wave equation. So we have to derive both the wave equations. But before going to Schrödinger's wave equation, we have to first understand what is wave function. So already we have discussed about matter wave. That means the waves which are associated with material particles in motion, they are said to be matter waves. Normally, if we consider any electromagnetic wave, light wave is nothing but electromagnetic wave. So when electromagnetic wave travels or propagates in medium, both electric field vector and magnetic field vector varies. Or in day-to-day life, you can see when wave created in water body, the height of the water gradually decreases, increases, and so on. In case of sound wave, compression rarefaction takes place, that is the pressure varies. Similarly, there must be some factor which varies in case of matter wave. So the quantity or the factor which varies in case of matter wave is known as wave function, and wave function is represented by the symbol psi. So wave function is the factor which varies in case of any matter wave or de Broglie wave. So wave function can be represented by psi r or it can be represented as psi rt. Then what is the difference between them? If it is only represented psi r, it defines only the position. Here it defines the complete knowledge with respect to position and time. If psi are given, then that is only position. Let the particle at x equal to 2. That means x equal to 2 is a constant quantity. But if we define the position of the particle with respect to time, let x equal to 2t square. So at putting different values of t, we can get the position of particle at different time. Similarly, psi r defines the position of the particle, only the coordinates or position. Psi rt defines the complete knowledge of the particle. That means with respect to position and time we can identify. And always remember, this is a complex number or complex function, complex quantity. So complex conjugate will be written like psi star complex quantity. So the probability is always psi into psi star integration maximum we can take infinity to infinity dv, or which is you can directly write on minus infinity plus infinity psi mod square dv, and probability, maximum probability, already you know that is 100%. Just like if we take a coin and we can toss it, the probability of finding head is 50%, probability of finding tail is 50%. So the total maximum probability is always 100%. So here the probability of finding the particle is always 1. This is all about wave function. Now we are using this wave function in order to derive Schrödinger's equation. So first we will discuss about Schrödinger's time independent wave equation. Time independent. So I think you remember the differential form of wave equation. In wave chapter we discussed already. In case of electromagnetic wave also we use that equation. Remember the transverse nature of electromagnetic wave? That wave equation we are going to use here. So the differential form of wave equation in terms of wave function psi is 1 del square psi equal to 1 by v square d square psi by dt square. Let the solution of this wave function psi is psi naught, which is function of r. This is psi means function of r and t both. Okay, and psi r is only function of position. E to the power minus I omega t minus kx. Here also you can write down plus kx because y equal to r sin omega t plus or minus theta. So plus kx means plus theta, minus kx means minus theta. Anything you can take. Now if we calculate derivative, d psi by dt, derivative with respect to t, this is a function of r, so this remains constant with respect to t. Now e to the power theta, formula will be e to the power theta omega t minus kx. Again we have to take derivative of this exponent term, which is equal to minus I omega. Clear? Minus I omega, derivative of t is 1 and derivative of kx is 0, so minus I omega. But here in equation 1 we have double derivative with respect to t, d square psi by dt square. Again if we take derivative, d square psi by dt square, then on the right side we will get psi naught function of r e to the power minus I omega t minus kx, then minus I omega was there. Again if we take derivative of this, again you will get another minus I omega, so this will be minus I omega whole square. Clear? Always remember, you can take this minus kx or you can also take this plus kx. There is no issue with that. Now we have to write down this. See this one, omega psi naught and this term except minus I omega. So this is nothing but psi rt. So you can directly write down psi rt there. So you can directly write down del square psi by d t square equal to psi function of rt, and minus, you can see here, minus square will be plus, I square will be I square, and omega square will be omega square. So I square, in case of complex number, I is nothing but square root of minus 1, so I square will be minus 1. This is nothing but minus omega square, minus omega square. Negative sign, its square will be plus, I square will be, I square is nothing but minus 1, so we use that here, I square is minus 1 omega square, so we get d square psi by dt square equal to minus psi omega square. Now you can use that value in equation number 1. Clear? Equation number 1, you can say del square psi equal to 1 by v square d square psi by dt square, and in case of d square psi by dt square we get minus psi omega square. We have to just use that in equation number 1. So if we use equation 1 was our d square psi function of rt equal to 1 by v square d square psi by dt square. This is nothing but minus omega square psi function of rt. So we get del square psi equal to minus omega square by v square psi. You can also omit rt, but omega is 2 pi nu and velocity is nu lambda. We can use that here. So if we use that here, we get del square psi, which is equal to, negative sign is there, in place of omega we can write down 2 pi nu square, in place of v we can write down nu lambda square and psi. Now we can cancel here, you can see we can cancel nu square you can cancel, so this will be like del square psi equal to minus 2 pi square, so 4 pi square, here we have lambda square psi. Clear? Now we can again use the de Broglie wavelength, lambda equal to h by p, which is equal to h by mv. This is the formula already we have completed, the de Broglie part. If we use that here, this will be like del square psi equal to minus 4 pi square. In place of lambda we can now write down h by mv whole square psi. Here we just use the wavelength for de Broglie wavelength or matter wave, which is equal to h by mv, its square, so this will be h square divided by m square v square, and m square v square will be converted to the numerator. So we get del square psi equal to minus 4 pi square m square v square by h square. Again I am again I am repeating this term. 4 pi square was there, h by mv square, so m square v square will be in the numerator divided by h square, and psi will be there, psi. But we know that h cross equal to h by 2 pi, so h cross square will be h square by 4 pi square. So in place of this term we can also simply write down h cross square. So del square psi equal to minus. This term is there, so you can write down m square v square divided by h cross square psi. If capital E is total energy and V is potential energy, V is potential energy, then kinetic energy will be total energy, that is the mechanical. So kinetic energy is nothing but total energy minus V square. So kinetic is nothing but half m velocity square equal to E minus, this is V, E minus V. We need here what? M square V square. So if we multiply one m here, this is m V square equal to 2 into E minus V. If we multiply one m here, this will be like m square V square equal to 2m E minus V. So you have to just use that here. So if we use, we will get del square psi equal to, see here, minus m square v square, but in place of m square v square we can write 2m E minus V by h cross square. 2m E minus V by h cross square whole into psi. Whole into psi. So minus h cross square, you can cross multiply here this term, or directly you can take left side, del square psi plus 2m by h cross square E minus V psi equal to 0. This is Schrödinger's time independent wave equation, because this term contains only derivative with respect to position. There is no term involved with respect to time. So it is said to be time independent. Again, for free particle, for free particle, potential energy 0, because the particle is free to move. So total energy will be due to kinetic energy. So V 0. So you can directly write down del square psi plus 2m by h cross square E psi equal to 0. This is a special case for free particle. This is time independent Schrödinger's wave equation. Yeah. Next we are going to discuss about time dependent wave equation, and time dependent wave equation we can derive from time independent. By using this equation you can derive. Now we are going to discuss about time dependent Schrödinger equation. So this is simply we can use the time independent one. So already we have used the wave equation psi rt as psi naught, which is function of r e to the power minus I omega t minus kx. Now if we take derivative with respect to t, only psi also you can write down, there is no issue. Okay, dt if you write, this will be psi naught function of r e to the power minus I omega t minus kx into minus I omega. Again if we rearrange, this term is nothing but psi rt. So you can write down d psi by dt equal to minus I omega. I omega is there, psi. Clear? I omega psi function of rt. But what is omega? Omega is 2 pi nu. Again nu equal to E by h, because E equal to h nu. So if we use that here, we can write omega equal to 2 pi. In place of nu, we can write E by h, and h by 2 pi is h cross, because h cross equal to h by 2 pi. This is just another constant. So we have here 2 pi by h. So you can directly write down h cross. So in place of omega, we can now write down E by h cross. So we will have d psi by dt equal to minus I omega was there. See, in the derivative term we have minus I omega, but in place of omega now we can use this form E by h cross. So minus I E by h cross will be there, minus I E by h cross into that psi. Psi is there, psi function of RT here. Then if we cross multiply here, this will be h cross by I, negative sign is there, d psi by dt equal to E psi function of RT. Now minus I, if we multiply one I in the numerator, minus h cross, if we multiply one I, then we have I is there, again we divide one I, d psi by dt, this is nothing but E psi RT. If we multiply one, divide one, I into I will be I square, I into I will be I square, I square is nothing but minus 1, minus minus will be plus. So we can directly write down I h cross d psi by dt equal to E psi. This is another form we get for the function E psi. We have to just use this value in time independent one. Already we have derived the time independent. The time independent was del square psi plus 2m by h cross square 2m by h cross square E minus v psi equal to 0. Already we have derived. Here you can see del square psi plus 2m by h cross square E minus v by psi. Here we have E into psi minus v into psi. In place of E into psi, we have to just use that value. So here we have to just, we can write that del square psi equal to minus 2m by h cross square E minus v psi. We can cross multiply here. This will be minus h cross square by 2m del square psi equal to E minus v psi, and this right hand side is nothing but E psi minus v psi, same thing. If we take to that this side, this is equal to minus h cross square by 2m del square psi equal to E psi. Already we have written what is E psi. This is equal to I h cross del psi by del t. We have to just use that there. This is equal to I h cross del psi by del t minus v psi. V term we can take to LHS. Minus h cross square by 2m del square psi plus v psi equal to I h cross del psi by del t. Here you can take psi common, so minus h cross square by 2m plus v into psi equal to I h cross del psi by del t. So this is time dependent, because here you can see del square was there, I left del square here. Del square was there, derivative with respect to position, but on right hand side you can see there is a factor which depends upon time, derivative of psi, that wave function with respect to time. Since it contains factors affecting derivative of t means with respect to t, this is said to be time dependent wave equation. Schrödinger's time dependent wave equation, and this whole term is also known as a parameter or operator which is known as Hamiltonian operator. This is also written as H. You can also write down that minus h cross square, you can see minus h cross square by 2m into del square minus h cross square by 2m into del square plus v is nothing but h. H is Hamiltonian operator. Just like del is an operator, this is also another modified operator. So you can write down h psi equal to e psi, also you can write down. From here you can see, if this whole term is h into psi equal to ih cross del psi by del t, ih cross del psi by del t, what? That is equal to nothing but e, that is e psi. So h psi equal to e psi. This is Hamiltonian operator. This is all about the derivation of Schrödinger's time dependent and Schrödinger's time independent wave equation. Thank you.